This is your presenter Asloob Mudassar, and I am presenting slide number 108 of the course on laser physics. Question is, derive the space-independent rate equations for a four-level laser system. Comment on the validity of the rate equations. The answer is, in the rate equation approximation, the derivation of laser equations are based on the concept that there should be a balance between the total number of atoms undergoing a transition and the total number of photons being created or annihilated. The results obtained from this theory are accurate and suitable for practical purposes. More accurate results will be based on semi-classical approach or quantum electrodynamics approach. A four-level laser scheme is shown in figure 108.1. The pumping is done from the ground level, that is level number 1, to level number 4, a single level or a band of levels. That is, the level 4 could be a single level or could be a band of levels. The level 4 must be a fast decaying level with the population in that level nearly zero. That is, the population of the N4 can be approximated to be zero. Level 3 is the upper laser level and level 2 is the lower laser level. Level 2 is a fast decaying level with the population in that level nearly zero. That is, the population of N2 can be approximated to be equal to zero. The figure shows a single stage pumping to the level 4. The pumping could be extended to levels 5 or level 6 provided they exist and that they decay rapidly to the level number 3, which is the upper laser level. So the scheme is shown in figure over here. That is in figure number 1, we have a typical scheme for a 4-level laser system. You can see that the pumping is done from level number 1 to level number 4. Level number 4 is a fast decaying level with a population nearly zero at all times. So it decays to the population level number 3, which is the upper laser level. The level 3 could be a single level or could be a band of levels coupled together. And then this level, then from level number 3 to level number 2, lasing action will occur. Because the population inversion is achieved in the level number 3 with respect to level number 2. Level number 2 is a fast decaying level. So the population of level 2 at any time could be considered to be zero. And we are also assuming, since the pumping is done from level number 1 to level number 4, we are also assuming that there is no decay of the population from level number 4 to the level number 1. So there is no decay, that is, it is prohibited. So only the decay of level number 4 is through the fast decay to the level number 3. Then from level number 3 to level number 2, we have the lasing action. And then the level number 2 is a fast decaying level and the population comes to the ground state. So the upper laser level is the level number 3 and the lower laser level is the level number 2 in a typical 4-level laser systems. So you see that we can also consider that there could be some upper levels, other levels above the level number 4, that is level number 5 or level number 6, and we can also perform the pumping to those levels. But ultimately, those levels should decay very fastly to level number 3 because we want to have the population inversion in level number 3 with respect to level number 2. Because we want to have a lasing action between these two levels because our required frequency lies in between the level number 3 and the level number 2. That is the resonance frequency or the frequency at the output of the laser beam. The population of level 4 and level 2 are nearly zero and the concentration should be focused on the populations of level 3 and 1. Level 1 is the ground level. We assume that only one cavity mode exists in the resonator. So you see that this is the assumption that we shall carry out throughout our lecture, unless at the end we speak about multi-levels oscillating within the laser cavity. So we should assume, we are assuming that only one cavity mode exists in the resonator. We further assume that the pumping and the mode energy density are uniformly distributed within the active medium. So you see that our calculations will be based on that. That is, the pumping is uniform and that the energy density is also uniformly distributed within the active medium. The rate equations derived under these assumptions are referred to as the space-independent rate equations, because we are assuming uniformity in the pumping process and also uniformity in the mode energy density. That's why we are calling it as a space-independent rate equations, which will be based on these two assumptions. These assumptions are met when the resonator is a unidirectional ring resonator and the transverse beam profile is uniform. So these, you see, that are the extra consequences due to these pumpings. In order to ensure the above two assumptions to hold and the validity to hold, we require that the unidirectional ring resonator should be there and that the transverse beam profile is uniform. Let phi gives the total number of photons in the cavity at any time t. The following two equations can immediately be written. One is the rate of a population of the level number 3, that is the dn3 over dt, that is equal to, on the right hand side we have rp, that is the pumping rate, minus b into phi into n3 and minus n3 over tau. We shall be explaining these terms shortly. And the next equation is d phi over dt is equal to, on the right hand side we have Va times B times phi times N3 minus phi over tau C. So we are explaining these two equations in detail in the next few paragraphs, where Rp is the pump rate and that there is a negligible decay from level number 4 to level number 1 under the pumping process. B phi N3, you see that B phi N3 is present. This term is present as a whole on the right hand side in equation number 1 and also is present in equation number 2 but multiplied by Va over there. So B phi N3 is the stimulated emission term. It gives the rate of a population decrease due to stimulated emission. You see that there is a negative sign over here in equation number 1 with this term, which means that this term would try to decrease the population of the level number 3, of the level number of the population present in level number 3. So B phi times N3 is the stimulated emission term. It gives the rate of a population decrease due to stimulated emission. Capital B is the stimulated transition rate per photon per mode. And tau is the lifetime of the upper laser level, accounting both radiative and non-radiative processes. And you see that tau is present in the denominator of the last term on the right hand side in equation number 1. So this is actually the spontaneous emission term. And the spontaneous emission term due to both radiative and non-radiative processes. If the upper laser level consists of many strongly coupled sublevels, so if the upper laser level consists of many strongly coupled sublevels, then tau is regarded as the effective lifetime. In such a case, we can represent tau is equal to the summation of all the lifetimes with the multiplication of appropriate weighting factors. So Ti is the lifetime of the ith sublevel and Wi is the corresponding weight factor. And we are here assuming that there are m sublevels. There are m sublevels present in the level number 3 or the upper laser level. So here we state that Wi is the weighting factor of the ith sublevel proportional to the population of that sublevel, and tau I is the lifetime of the ith sublevel. VA times B times phi times N3. So this term is present on the right hand side in equation number 2. So let me show you the position of this term. So this term now we are talking about VA times B times phi times N3. So this is present in the rate equation of photons. So Va times B times phi times N3 gives the photon growth rate, because the decrease in population proportionally increase the photon number, and Va is the volume of the mode present in the active medium. Phi over tau C accounts for the removal of photons due to cavity losses, and tau C is the photon lifetime due to cavity losses. So C stands for the cavity. So tau C is the photon lifetime due to cavity losses. Let us analyze the contribution of the spontaneous emission photons in equation number 1 and equation number 2 one by one. So now in the next paragraph we are going to concentrate on the spontaneous emission of photons in equation number 1 and equation number 2, but consider them one by one. Spontaneous emission also occurs along with stimulated emission, and it decreases the population rate of the upper laser level, and the term minus times n3 over tau r, the negative sign shows that the population of the level n3 will decrease due to the spontaneous emission, and tau r is the radiative lifetime of level number 3. So this term, which is minus n3 times over tau r, must be present on the right hand side in equation number 1, but has been omitted because the presence of the term minus n3 divided by tau accounts for the term minus n3 over tau r in an implicit manner. So you see that this term, that is minus n3 over tau, is actually taking care of this term, which is a minus n3 over tau r, that is the decay in the population of level 3 due to the radiative process. So the term which is present in our equation number 1 on the right hand side, which is minus n3 over tau r, which is minus n3 over tau, shown in red, actually this term is taking care of this term, which is minus n3 over tau r, in an implicit manner. The contribution of spontaneous emission photon on the right hand side in equation number 2 should be due to Va times n3 over tau r. So let's see that is this term is present, that is Va times n3 over tau r in equation number 2. You see that this term is not present. So what about this term? The contribution of the spontaneous emission photons on the right hand side in equation number 2 should be due to this, that is Va times into n3 over tau r, which is not correct. That is, the presence of this term is not correct, because the spontaneous emission occurs in the 4 pi angle and covers the entire frequency range. Whereas the effect of this term is that only those spontaneously emitted photons should be considered which travel along the direction of the stimulated photons and have the same spectral width as that of the stimulated photons. So you see that if we include this term over there, it means that we are considering the only those spontaneously emitted photons which travel along the direction of the stimulated photons and have the same spectral width as that of the stimulated photons. So the inclusion of this term is not appropriate, because we shall see that when the lasing action starts, this term becomes insignificant. And moreover, this term, as we said, that this term is incorrect because the spontaneous emission occurs in a 4 pi angle and covers the entire frequency range. So due to that one, the inclusion of this term is not appropriate. Once the lasing action has started, the contribution of the spontaneously emitted photons with characteristics similar to those of the stimulated photons is negligible. It is important that at least one spontaneously emitted photon was present in the cavity responsible for the onset of the lasing action. According to the quantum electrodynamics approach, a term Va times B times N3 should be present on the right hand side of equation number 2 to account for the spontaneous emission process. But we have neglected it for the reasons given earlier. So you see that the reason is the same as we have mentioned in this paragraph. That why we have neglected that term. So the reason has been given. So that's why we cannot include the term Va times B times N3 to account for the spontaneous emission process. So to see that we have all explained all the terms in equation number 1 and equation number 2. Especially we have explained well the spontaneous emission terms, that which terms have been included and which terms have not been included, and we have also given the appropriate reasons for them. Now the next step is, let us now derive expressions for capital B and tau c. Consider a resonator of length capital L containing an active medium of length equal to small l having refractive index equal to small n. Let capital I is the intensity of the traveling beam at a time t is equal to 0 within the cavity, and let I prime is the intensity after one round trip within that resonator, which can be written as, that is I prime, that is the intensity after one round trip, is equal to I times R1 times R2 times the square of 1 minus Li and times e to the power 2 sigma n3 times L. So this is the equation. This will give you the intensity expression after one round trip as shown in equation number 3, where capital R1 and capital R2 are the power reflectivities of the two mirrors. Capital Li is the single pass internal loss of the cavity, and square of this quantity, that's the square of 1 minus Li, is the round trip cavity transmission. So 1 minus Li is actually the transmission, and the square of that one is the round trip cavity transmission. 2 sigma times n3 times L is the round trip gain of the active medium. If you want to have a detailed of such expressions, I have also derived these expressions in one of the initial slides. So have a look on these slides to see the details description of such equations. Because I have discussed 3-level laser, 2-level laser system, 3-level laser systems, 4-level laser systems in some previous slides. If the upper laser level is degenerate or consists of many strongly coupled sublevels, the sigma will be modified and will be replaced by a new sigma effective, represented by sigma EFF, which we call as the effective sigma. If T1 and T2 are the power transmissions of the two mirrors, with A1 and A2 are the corresponding fractional mirror losses. So A1 and A2 are the fractional mirror losses. Then we have the following relationships. That is, capital R1 can be written as 1 minus A1 minus T1, which is equal to 1 minus A, because we have dropped the subscript with A. So 1 minus A minus T1, and this can be approximately written as in the product of two parentheses. One parenthesis contains 1 minus A, the other parenthesis contain 1 minus T1, and similarly we can write R2 is equal to 1 minus A2 minus T2, where A2 can be represented by A, and we have 1 minus A minus T2, which is can also be written as the product of two parentheses, which contains 1 minus A and 1 minus T2. where we have set a1 is equal to a2 is equal to a, that is we have considered that the fractional mirror losses for the two mirrors are identical, and that a is a small such that a is small such that we can write it 1 minus a times t1 is approximately equal to 1, and 1 minus a times t2 is approximately equal to 2. We have used these two approximations in writing the expressions for r1 and r2. Let's calculate the change in intensity delta I for one cavity round trip, and that is given by delta I is equal to I prime minus I, and that can be written as by substituting the values of I prime over here in terms of the parameters, that is we have used the values of r1 and r2 from the above equations in writing the expression for I prime. So we have these expressions, and you see that we have at the end we have multiplied it with capital I outside the curly bracket. And you know that in the writing equation number 4, we have used R1 and R2 in the expressions of over here in equation number 3. So we have used the values of R1 and R2 in these equations, and then we have made the subtraction. And you see that we have capital I outside the curly bracket on the right hand side. So this expression gives you the change in intensity after one cavity round trip. To write this equation in a compact form, keeping in view the presence of the exponential terms, that is e to the power 2 times sigma times n3 times L, we introduce gamma as the logarithmic loss per pass as given. Gamma 1 is equal to minus log of 1 minus t1. Gamma 2 is equal to minus log of 1 minus t2, and gamma I is equal to minus, within the square bracket we have log of 1 minus a plus log of 1 minus li. So these are the three losses that we have represented in the form of logarithmic loss per pass. So we have introduced gamma 1 and gamma 2 and gamma 3 so that we can write the equation number 4 in the simplified and compact form. And we are now going to explain what gamma 1, gamma 2 and gamma I are. So you see that gamma 1 and gamma 2 are due to mirror transmissions. Losses, logarithmic losses due to mirror transmissions, and gamma I is due to the internal cavity loss and are simply called as mirror losses and internal loss respectively. So gamma 1 and gamma 2 may be regarded as may be labeled as mirror losses, and gamma I may be regarded as the internal cavity loss. So now equation number 4, by introducing the values of gamma 1, gamma 2 and gamma I, can be written as delta I, that is the change in intensity after one round trip, is equal to in the parenthesis we have e to the power 2 times of sigma times n3 times L minus gamma subtracted from it, minus 1 is subtracted from this exponential term, and then outside the parenthesis we are multiplying it with I, that is the intensity in the present in the laser cavity at an instant of time t is equal to 0, where capital gamma, which we have introduced in the exponent term, is gamma is equal to gamma I plus gamma 1 plus gamma 2 divided by 2, as shown in equation number 6. So gamma is actually the total logarithmic loss per pass, expanding to e to the expanding this exponential term, which is e to the power 2 sigma and 3 times L minus gamma, into the power series, assuming that sigma times and 3 times L minus gamma is small compared with 1. In the expansion, the squared term and the higher power terms can be neglected. So we can keep only the first two terms in the expansion of this one. So the squared term and the higher order terms will be neglected. Due to the first two terms, the first term will be equal to 1, which will be cancelled out by this minus 1 term over here in equation number 5. So only we shall serve the second term in the exponential, then will survive because the higher terms have been neglected. So we are writing delta I is equal to 2 times of sigma times N3 into L minus gamma and then multiplied by L outside this parenthesis, multiplied by this intensity I outside this parenthesis as shown in equation number 7. So this is the compact form of the which gives you the change in intensity after one round trip. Dividing both sides by the time taken by the light to complete one round trip, which is delta t, and delta t is equal to 2L naught over C, because L naught is the total length of the cavity, and we have time to travel one round trip. Delta t is equal to L naught over C, where L naught is the optical path length of the resonator, and L naught can be written as, can be splitted into two parts. That is, L naught is equal to capital L plus capital L minus L minus small l. Capital L minus small l will give you the part of the resonator which is outside the active medium, and then we have n times small l will give you the length of the active medium within the resonator. So we have L naught is equal to capital L times n minus 1 times small l. So introducing this one under the approximation, that is, we are dividing both with delta t. So we have delta I divided by delta t. Since delta t is very small, for one round trip we can approximate it to be equal to di over dt. So we get we can write equation number 7 now in the form that di over dt, that is the rate of change of intensity with the time, is equal to, the rest of the quantities are the same except that we have divided it with delta t, introducing 2L naught divided by C in the denominator of these is denominator on the right hand side. So we have simplified result is sigma C into L divided by L naught. This term is multiplied by N3, and then we have a minus gamma C over L naught. Then this parenthesis terms in the parenthesis is multiplied by the intensity I. Or we can also write in a more logical form so that we can explain the other terms. That is d or di over dt. We have multiplied by the first term has been multiplied by va shown in red and also divided in the denominator by va. So the rest of the quantities are the same, and except that we have also multiplied by the intensity on the right hand side of this term. You see that the intensity I is present. We are multiplying now. We are expanding this parenthesis, multiplying with I to each of the terms, and then the first term has been multiplied and by divided by with the capital VA. The rest of the things are the same, but rearrangement of the terms has been done. And then the second term on the right hand side is minus I over, we have L naught over divided by gamma C. Now you see that photon is proportional to the initial intensity. So phi is proportional to I, or phi can be written as omega times I, where omega is some constant. Now substituting in equation number 2 and dividing the resultant equation by gamma, we obtain. So we have obtained equation number 9 from equation number 2 by introducing phi by gamma times I, and then dividing the whole equation, both sides of the equation, by capital gamma. We have obtained this equation from equation number 2 shown in equation number 9, which is the di over dt is equal to Va times d times I times n3 minus I over tau c. So you see that here now we can we have two expressions of di over dt. One is shown in equation number 8, the other is shown in equation number 9. We can compare the two equations, and for the value of capital B and tau c. The value of a capital B can be directly written by the comparison, that capital B is equal to sigma times C times L divided by VA times L naught. And then we can write it further simplified result is sigma C divided by capital V, where capital V can be written as capital V is equal to L naught divided by small l, and this whole multiplied by VA. So this capital V can be labeled as mode volume within the laser cavity. So this VA This V can be labeled as mod volume within the laser cavity, and by comparison, we can also find the value of tau c. So you see that if you compare these two equations, the last two terms on in equation number 8 and 9, you can find out immediately the value of tau c, which I have written as tau c is equal to L naught over gamma c. And you know that tau c is the lifetime of the photons in the cavity. So we have obtained the value of capital B, we have obtained the value of tau c, which were unknown in the first two equations. This gives the photon lifetime in cavity parameters. So we have obtained lifetime, that is the photon lifetime tau c, in terms of the cavity parameters. And the cavity parameters that appear in the expression of the photon lifetime is the L naught, that is the length of the resonator, divided by the gamma, and c. C is the velocity of light, and gamma is the total loss within the resonator for one pass. So this gives the photon lifetime in cavity parameters. Since the population in the level 2 of the laser of the 4-level laser system can be assumed to be zero, the population difference between the laser levels can be written as, that is n3 minus n2, can be approximated to be equal to n3, because the population of the n2 can be assumed to be zero. This population inversion can be assigned a new symbol capital N, and thus the rate equations can be written as. So we can write the rate equations shown in equation number 1 and 2 respectively can now be written as in terms of the new symbol capital N, which represents the population inversion, which represents the total population due to the population inversion, is dn over dt, is equal to, on the right hand side we have rp minus b times phi times n minus n over tau, and the second photon rate equation is d phi over dt is equal to, within the parentheses we have va times b times n minus 1 over tau c multiplied outside with phi. These two equations can be used to describe the first order behavior of a 4-level laser system in the continuous wave and transient cases. These space-independent rate equations are useful for the basic understanding of laser behavior, and in the continuous mode, the results are close to more complicated space-dependent rate equations. So you see that we are not writing the space-dependent rate equations, but if we could write those equations, we shall see that the above equations for the case of continuous mode are much similar to the more complicated derivations of the space-dependent rate equations. And you see that we have written down the above equations only for the case of a single mode. But you know that if there are m oscillating modes, that is the m longitudinal modes are present in the laser resonator, then we need two m equations. M equations of the type shown in equation number 13 and m equations of the type shown in equation number 14 are required to fully describe the system. That is, for m mode we need two m equations of the type shown in equation number 13 and m equations of the type shown in equation number 14. If the mode oscillates with the random phases, so you see that as we are now commenting that if many modes are present, the modes could have different phases. So if modes are oscillating with the random phases, the overall beam intensity at the output is the sum of the intensities of the individual modes. So you see that this is a addition, that is this addition is on the basis of the intensities, not on the basis of the amplitudes, because the phases are random. The overall beam will have a uniform profile if the active medium is pumped uniformly in the transverse mode. So you see that again we are talking about the same assumptions on which we derived our equation. That is, the overall beam will have uniform profile if the active medium is pumped uniformly in the transverse mode. The total photon number is the sum of the photons related to each mode, and a single photon rate equation in phi can thus be used. You see that for the addition of the total number of photons, we don't bother about whether the photons are in phase or out of phase. We can just add them together, and we can only a single photon equation will be sufficient. In a laser with a large gain, the counter propagating waves, you see that now we are discussing a special case, large gain case. The counter propagating waves have strong dependence along the resonator axis, and similarly the population inversion has also such a dependence. The intensity in equation number 3 should also show this dependence, that is the large gain. So you see that we have not discussed the large dependence, that is when the gain is very large over equation number 3 does not speak anything about that. So if we are talking about a very large gain, the intensity in equation number 3 should also show this dependence. The rate equations valid for the case of homogeneously broadened line. So you see that the rate equations in equation number 3 and equation number 4 are well valid for a homogeneously broadened line. But you know that if we are going to discuss the inhomogeneously broadened line, in the case of inhomogeneously broadened line with the absence of Doppler effect, so ignoring the Doppler effect, but the homogeneous broadening is there, and we are ignoring for the time being the Doppler effect. Laser beam with a single frequency will interact with the excited species having a resonance frequency equal to the laser frequency. At a high frequency, at a high intensity, a hole will appear at the location of the laser frequency in the saturated gain profile. We have also discussed the hole burning process in one of our previous slides. So here we are just commenting that at a high intensity, a hole will appear at the location of the laser frequency in the saturated gain profile. The assumptions that the total population present in the upper laser level, which we have assumed to be equal to N3, will no longer be valid, because due to hole burning at a specific frequency, the populations at that level will not be, you see that will be missing, and we cannot write the total population in the upper laser level to be equal to N3. If the Doppler effect, now if we include the Doppler effect is taken into account, the laser frequency will be different from the central transition frequency. Because you see that now the many frequencies could be present in the cavity due to the Doppler effect, and the laser can operate at one of those frequencies. The two counter propagating beams will see different atoms or molecules on their way. For continuous wave operation, the time derivatives in both the rate equations is set to 0, because the continuous wave operations mean that the intensity is not changing with the time, and we can set di over dt equal to 0, and similarly the photon numbers are not changing, we can set d phi over dt is equal to 0. And this will hold for the continuous wave operation. To find the transient behavior, we can set Rp to be equal to Rp as a function of time, and use the known initial conditions that initially the population of the upper laser level is 0, and initially the number of photons in the cavity to be present is equal to phi I, where for the simplest case we can choose that phi I is equal to 1, that at least one photon was present in the laser cavity before the initiation of the lasing process. So these may be reasonable options that we have chosen. The power output from one of the mirrors can be found using. So you see that for the output from one of the mirrors, we can choose the 1 over tau c to be equal to gamma times c divided by L naught. And this we can split into three parts, that is gamma I into c over L naught plus gamma 1 into c over 2 L naught plus gamma 2 into c over 2 L naught. So we can introduce 1 over tau c in equation number 14. And there we can recognize this term, that is gamma 2 multiplied by c divided by 2 L naught, and this parenthesis times phi as the rate of photon loss due to transmission through the mirror 2. Because gamma 2 corresponds to the logarithmic loss through the mirror 2, and this will give you the rate of photon loss due to the transmission through the mirror 2. And if you want to calculate the output power, you need to multiply it this rate with the photon energy. So we have output power given by this expression shown in equation number 5, and on the right hand side we have the rate of photon loss from the laser cavity, which is gamma 2 times c divided by 2 L naught multiplied by phi. This is the rate of photon loss from the cavity, and then we have multiplied with h nu, which is the energy of one photon, that is the energy of each photon. So this overall give you the output, total power output from the laser source. So you see that we have briefly explained the time independent space equations derived for the 4-level laser systems, and we have explained, we tried our best to explain all the relevant terms, and we have also given some commentary on each of those terms. I hope the lecture will be beneficial. So this is the end of slide number 108.